All right, welcome everyone. I am JJ. Let's do an example problem. So we have a frame consists of pin connected members AB and BC. So just two things we pinned together. It's externally supported by a fixed support at A and a roller at C. Let's determine what's going on everywhere at A, B, and C. If I'm finding reactions, I know I need equilibrium equations. I'm applying equilibrium. I need to have free body diagrams to go with this. So let's start out and just draw a real quick overall free body diagram. So our overall FBD. If we start there, we're going to have just a straight line that goes from A all the way out to C. At A, I should put in, I have a fixed support, so I need an AY. I need an AX. I'm going to assume it goes to the left. AX. And the one thing people tend to forget for a fixed support is fixed supports resist moment. So I also have to put in here a moment, an applied moment. Let's call that MA. Out at point C, I have a roller. So I should have one force perpendicular to what it rolls on, perpendicular to the ground, be straight up and down. A CY in there. Point B is internalized. If I'm drawing my entire free body diagram, I'm not separating anything out at B. BX and BY, well, they exist, don't matter in my overall free body diagram. I just need to get in that triangular distributed load in here. Go straight down off of this. And my triangle goes up to a max height of 260 pounds per foot. My width in here, if point B doesn't matter for us, I can just add 8 and 5 together. The entire width here is 13 feet. Right now I have AX, AY, MA, and CY, 4 unknowns in here. I can't find all of these. So really what we should ask ourselves then is, can we find any of them? On this one, I can't do forces in the Y. I'd have 2 unknowns. I only have 3 equations total. I can't sum moments because no matter where I sum moments at, I would have either AY or CY or both of them, but also MA in my equation. MA will always show up in a moment equation. In the X direction, I have AX, and the force I forgot to label, 200 pounds to the right. 200 pounds. That's no, I could find AX in here. So let's actually start there. If I sum my forces in the X direction, I'd have 200 going to the right minus AX equals 0. Again, we're making a full equation, even when it's a really easy one for us to solve out because it builds good habits and it's actually going to set us up to be way more successful. Solving that, I'm going to get AX is 200 pounds. I get a positive number from my equilibrium equation when I solve it for AX, which means in my free body diagram, I guessed the right direction. It is to the left. So we'll get our arrow in there, getting magnitude and direction labeled. That's it for us. I can't find AY, CY, or MA at this point. I'm kind of at a standstill with this free body diagram. So we just want to explode our frame into individual pieces and try to go from there. If we think this through, if I drew a free body diagram of just AB, I would have AX, AY, MA. AX is known, so 2 unknowns so far, but at B I'd have BX and BY. 4 total unknowns. I have 3 equilibrium equations. If we can avoid it, let's start somewhere else. If I drew a free body diagram of BC, I would have BX, BY, CY. That's only 3 unknowns. I should be able to find all of them. So let's come in and tackle that. We'll draw a free body diagram of member BC. We can do just a straight line. It's 8 feet wide. 8 feet. At C, I have my roller, so a CY going straight up. I'm assuming the same direction I had before. CY I already guessed went up. Don't change that around. My 200 pounds should be going to the right. 200 pounds. And then I have a distributed load on here. We're going to start here not at 0 because at point B, I have some height in here. I've already grown a little bit in this. So I'm going to have to draw a trapezoid on this. My original height, I don't know at this point. We'll find it though. But my maximum height at the right edge is 260 pounds per foot. 260 pounds per foot. And the small height, let's come in and call that WO, the height at the beginning of our trapezoid. I can also say that at the left edge of this, I have a pin connecting member AB to member BC. A pin should have a Y component, so I'm going to guess BY goes up, and an X component. So I'll put in a BX for that one. Again, 3 unknowns, I should be able to find all of those. We just want to lay out equilibrium. So let's go ahead and get our X in here first. If I sum my forces in the X, I would have 200 to the right minus BX gets us to 0. Or if I solve that for BX, BX is 200 pounds. I get a positive from this, so I assume the right direction. It's to the left. There's that internal connection. I'm attaching members together, so I want to say on a specific member. That was when I was looking at member BC. So on BC. Because if I drew a free body diagram of AB, BX would still be there. It'd still be at 200 pounds. It'd be equal, but my direction would change around. Equal and opposite reactions. Again, it's just Newton's laws is all that we're applying on that. So we're including which member we're taking a look at here. From here, though, I need to figure out W0. So let's come over to the side and try to make a triangle out for this. I'm actually going to draw 2 triangles. One is my entire distributed load. So it has a base of 13 and a height of, I get up to that maximum height of 260. 260. And there's some angle in here, theta we'll call it. The actual angle doesn't matter for us in here. We won't work with that. We'll work with the tangent of this. But I can say if I truncate this somewhere in, maybe I truncate it 5 feet in, I would have a triangle that goes over, well, it just goes over 5 feet this time. 5 feet and up some height where I broke that 5 feet in, I'm at W0. So my height here is W0. And there's the same angle, theta. I'm using what's called proportional triangles in here. If it's the same angle theta, then my ratio of height to base, or base to height if I wanted to find a distance, has to be the same. So I could really say 260 over 13, 260 divided by 13, has to be equal to WO over 5. Because this is the same slope for the hypotenuse, I've just truncated it at B rather than showing the whole thing in here. My angle is still the exact same for that. So our tangent, opposite over adjacent, is the same. Really, this is tan theta equals tan theta is all I'm writing out here. Except I can solve that for WO and get that it is 100 pounds per foot, which gives me my WO at the start of my trapezoid here, or if I drew member AB, it would give me WO at the very end of the trapezoid, or at the end of a triangle in there, which is where we're going to go right after this. But just using proportional triangles. That becomes a really important thing. It will show up even in professional engineering practice. Using proportional triangles makes things a lot easier for us. And with that known, I can now come back and say, why don't I sum up my moments at B? With positive going counterclockwise, positive going counterclockwise, I'm going to sum my moments up about point B. If I'm doing this, I don't want to work with a trapezoid. Let's split this into 2 areas. We'll have one that is a rectangle and a second that's a triangle stuck on top of it. So this would be area 1. The triangle we'll call area 2. But summing moments, I would have CY will cause a counterclockwise rotation. So we'll put it in as positive. My distance is 8 CY. My rectangular distributed load will cause a clockwise rotation. So minus force times distance. Force for a distributed load is the area. My area is 8 times WO. 8 base times my height. WO, 100. 8 times 100. Force times my distance from B to, for a rectangular distributed load, we're measuring to the very center of the distributed load. So half of 8 times 8 over 2. And then we can go to the triangle. It will also cause a clockwise rotation, so minus area is my force, 1/2 base 8 times height. I want my difference between the tall side of the trapezoid and the small side because my triangle starts at 100, WO in there. So we'd say 260 minus 100. And then times my distance from the 90-degree corner or from B to a third of the way in from that 90-degree corner. So I'd have times 8 gets me from B to the 90-degree corner minus a third of the way into it. 8 thirds gets us to 0. Again, for a triangle, our distance goes a third of the way from the 90-degree corner. Technically, 8 minus 8 thirds, just to acknowledge this, is 2/3 of the way in. We could remember it's 2/3 from the pointy side of the triangle. I just try to remember one rule because the more things I have to memorize, the more likely I am to confuse them and do it wrong. So I try to always just do a third of the way in from the 90-degree corner. But there's no reason we have to do it that way. We could do 2/3 and we get to the same point. Either one. But CY is my only unknown here. If I solve for CY, I'm going to get 826.7 pounds going up. I'm going to get a positive from this, which means I guessed the right direction. Which would be my second answer, or third, actually. With that known, I can now sum forces in the Y direction. If I sum forces in the Y, we'll get our free body diagram here. For summing forces in the Y, I would have BY goes up. I would have CY, I know is going up, plus 826.7 minus area 1, the force from our rectangular distributed load, will be minus base times height. 8 times my height, WO, is 100. Minus the area of area 2. Minus, that's our force piece, 1/2 base, 8, times height, 260 minus 100. 260 minus 100, or 160, is going to get us to 0. Equals 0. If I solve for BY here, I'm going to get a positive, so I guess the right direction here, that BY is equal to 613.3 pounds. We're going up on, remember, BC. On BC. I got a positive number out for this, so I guessed the right direction of my free body diagram. It's going up when we're looking at free body diagram BC. Getting that magnitude, direction, and on a specific member for our internal connections. But that gives me 3 things that I just found with free body diagram BC. That's all I can get there. I have to go somewhere else then. I could go back and work with this overall one. Now that I know A or CY, I've already found CX. So I've used one of my 3 equilibrium equations. I have 2 left. But I could come in here in some moments about A. That would give me MA. And then I could do forces in the Y. That would give me AY. This is a solvable thing using that. Or I could come in and draw a free body diagram of AB and do a similar approach. I'm going to work with AB in here, just so we can illustrate one more thing. So if we draw a free body diagram of AB, remember we've said for an internal connection, like what we have here at B, if I move from one free body diagram to the next, I have to make this be equal and opposite. So my direction is going to change because I'm moving to a new member. So at AB, I would have just a horizontal member in here. We have a triangular distributed load. We don't get all the way up to the max height on that. We're not getting to 260 because we're truncating this at point B. We're getting to W0. We already found how tall this was at B. So this is 100 pounds per foot. At A, I already guessed directions. We aren't going to change our support directions around. We're basically already finding it on the member. We don't move to a new member with that. So I'd have AY going straight up. I would have AX going to the left. We already found was 200. I would have MA, I assumed was counterclockwise before, so that should still be true. MA. This width is 8 feet, or 5 feet. 5 feet. So I'll get that in. And then the ones that mess people up. We had BX was to the left on BC. We've now moved to a new connection point. It should be equal and opposite. So instead of going to the left, it's going to the right. That's the opposite. But equal, it's still 200 pounds. For every action, there's an equal and opposite reaction. We're just applying Newton's laws here. So it's 200 down. Same thing for BY, it should be equal and opposite. If it went up on BC, we're now going down here on AB. So down 613.3 pounds. Equal and opposite as I'm moving from one member over to the next in here. That's really why we're saying on a specific member for this, because those ones are going to change direction for us. It really just helps us clearly articulate what are we even looking at when we say this. Let's come in and apply equilibrium here. I don't need to do anything in the x direction. We are in equilibrium though. 200 minus 200 does get us to 0. That's it for us though. I can get AY. Let's just sum forces in the y, and we'll get there. If I sum my forces in the y direction, summing forces in the y, I have AY going up. BY is coming down, even though it was going up on BC. New member, new direction, equal and opposite. So minus BY, minus 613.3. Minus our triangular distributed load. Minus the area, we would have minus 1/2. My base is 5. And my height is 100. And that's all my y forces. This equals 0, which I can then solve for AY. And I'm going to get the area, or AY, is 863.3 pounds. I get a positive number from this equation, so I have the right direction here on AB and on the overall free body diagram. Both of those would tell us we are going up. And if I had worked with that overall free body diagram, this is exactly what I would have ended up getting for my answer on everything. Still 863.3. We will get to the same final point no matter what free body diagram, assuming we aren't making a mistake. We're taking a valid approach. And my last thing I need is that moment with positive going counterclockwise. If I'm looking for a moment, I have to use a moment equation. So summing my moments, and I can sum my moments about any point I want to, and it's still going to show up in here. I'm going to sum my moments about point A. Summing my moments about point A is going to get me, well, that moment that I'm resisting is a variable in here, equals MA. Minus my moment from BY, minus force 613.3 times my distance is 5, minus the moment from my distributed load, minus 1/2 base is 5. Height is going to be 100. That's my force of the triangular distributed load times my distance. We want to measure distance from A to a third of the way into the triangle from the 90-degree corner. So we'll go over 5 to get from A to the 90-degree corner, and then come back, so subtracting a third of their distance, 5/3. That's going to get me all the way to 0, not to 6, equals 0. MA is my only unknown in this. If I solve for it, I get a positive, which means I guessed the right direction at every point in here, making that consistent assumption. But I'm going to get the MA is 3,900 pound-feet. That's our magnitude. And our direction is counterclockwise for that. We got a positive, so the direction was correct in there. Really, this is the same approach on frames when we have distributed loads as when we don't. It's just complicating a little bit because we're dealing with distributed loads now. We can tackle these. There's more examples available. Hopefully this was useful for you. If it was, hit those like and subscribe buttons. Stick around and check out more videos. Let's get you an A with JJ.